In this video, we're going to use some fundamental trigonometric identities that we already know to simplify different expressions and prove different identities. The identities we need for this video are our reciprocal identities. Those are the ones that are like cosecant of theta is 1 over sine of theta, and so on. Our quotient identities, like tangent of theta is sine over cosine. Our Pythagorean identities, sine squared plus cosine squared is 1, tangent squared plus 1 is secant squared, and 1 plus cotangent squared is cosecant squared. And then we also need to know all of our even and odd properties of our trig functions. Remember that all of the trig functions are odd, meaning that like sine of negative x is negative sine of x, except for cosine and our secant. Those ones are even. So like cosine of negative x is positive cosine of x. Those are all we need in order to simplify these. The rest of the video is just a bunch of examples showing how to use these basic identities. So let's just start right away with a simplifying example. Let's simplify tangent of x times cosine squared of x times secant of x, and write it in a way that has no fractions and it's as simple as possible. But what I would do to simplify this guy is just use one of my quotient identities first. Tangent of x is equal to sine over cosine. Then I still have my cosine squared. In secant of x, I can use one of my reciprocal identities. I know that's 1 over cosine of x. But now take a look at what this looks like. This means when I multiply it all together, I have sine of x, cosine squared of x, over cosine squared of x, and then I can cancel those out, and this simplifies down to just sine of x. And so we rewrote a fairly complicated expression just as sine of x, just by using our quotient identities, our reciprocal identities, and that's really about it. So one way to simplify trig expressions is to rewrite in terms of sine and cosine and just see what happens from there. Another example. Let's say I want to simplify cosine of theta over sine of theta plus sine of theta over 1 plus cosine of theta. And I want to write this without using any fractions and write it as simple as possible. Well, I have two fractions being added together right here. So my instinct is to rewrite with a common denominator and add it together to one fraction. So if I do that, my first guy, I would have to multiply by a 1 plus cosine of theta on the top and the bottom. And my second fraction would need to be multiplied by a sine of theta on the top and the bottom. So that gives me a sine squared theta on the top. And there, now both my fractions have the same denominator, so I can add across the top. So I have cosine theta times 1 plus cosine theta plus a sine squared theta all over my sine of theta 1 plus cosine of theta. And right now, this doesn't look like it's getting any simpler, but it's going to. Now I can distribute this cosine of theta. Let's see what we get from there. So when I distribute that, my numerator is now cosine theta plus cosine squared of theta plus sine squared of theta all over my denominator, which is sine of theta, times 1 plus cosine of theta. Well, now there's something we can do to simplify this. In the numerator, I have cosine squared plus sine squared. That's one of my Pythagorean identities. Sine squared plus cosine squared is 1. So I can replace this cosine squared theta plus sine squared theta with a 1. Now it's getting much simpler because my numerator is cosine theta plus 1, and one of the factors in my denominator is 1 plus cosine of theta. Those can cancel out, and I just get 1 over sine of theta. But this unfortunately still has a fraction, so it's not as simple as it can get, but we do have our reciprocal identities. 1 over sine of theta, that's the same thing as cosecant of theta. And so that original expression that we have is a complicated way of just writing cosecant of theta. All right, let's do another one. I personally think these are kind of fun, just playing around algebraically, using what we know to rewrite things in an easier way. So let's simplify. 1 minus secant squared of t all over tangent of t minus tangent t secant t. And how would I want to maybe simplify this? Well, we're going to have to do some algebra, and we've done some different algebra techniques so far. We've just written things as sines and cosines. We have found a common denominator, and something that's very common in algebra that we haven't tried yet is factoring. And that's actually what I would do on this one. I notice in my denominator, I have a tangent t in common with both those terms, so I can factor it out. And in the numerator, I have a difference of squares, so I can factor that. So if I factor everything, my numerator is 1 minus secant t times 1 plus secant t. And my denominator, I can pull out tangent t, and I have 1 minus secant t left behind. And so that can cancel out. And I just have 1 plus secant t on top, tangent t on the bottom. But now we can simplify some more. This is simpler than where we started, but I don't have it as simple as possible. I still have a fraction, it's still a little complicated. So now let's rewrite this using sines and cosines and see if we can simplify it more. So secant is the same thing as 1 over cosine, and tangent is sine over cosine. And right now that looks absolutely terrible. But remember that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So let me rewrite it that way. I would have 1 plus my 1 over cosine of t times the reciprocal, which is cosine of t over sine of t. Now I can distribute. And when I distribute that, I have cosine t over sine t plus a 1 over sine t. And we still have fractions, but now I can just use my quotient identities and reciprocal identities to recognize that this is cotangent of t plus cosecant of t. And now it's written as simply as possible. I don't have a crazy fraction anymore. There's no powers of our trig functions, nothing that can be factored. It's about as simple as it can get. All right. So we've had some practice simplifying some things. Now let's try to verify some identities. So in a way, we're going to be proving that these identities are true. using just the knowledge that we have. So if you're asked to verify an identity, and they give you an identity to prove, like sine of negative x times cotangent of negative x over cosine of x equals 1, what you're going to want to do to try to prove this is work with the most complicated side. Just manipulate it algebraically, like what we've done in the previous examples, until you end up with the right side of the equation. So the first thing that stands out to me on this one are these negative x's inside of the sine and the cotangent. Now both sine and cotangent are odd, so I'm going to use the odd property of those functions to rewrite this left-hand side as negative sine of positive x times a negative cotangent of positive x all over cosine of x. Now the negative times the negative will make it positive. So I have sine x cotangent x over cosine of x. And from there, I would rewrite cotangent as cosine over sine. So I have my sine times cosine over sine all over cosine. So the sines get to cancel out in the numerator, leaving me with just cosine of x over cosine of x, which simplifies to 1, which was the right-hand side of what I was trying to show. So all we did was take the left-hand side of the identity we were to prove and just manipulated it using all of the identities we know and properties of our trig functions until we got the right-hand side. Let's do another one of those. Verify the identity, and I have 1 over 1 minus sine of x minus 1 over 1 plus sine of x is equal to 2 times tangent x secant x. So what would you do on this particular one? Well, I would start with the left-hand side again, because those fractions make it a little complicated. I'm going to manipulate the left-hand side algebraically and hopefully get the right-hand side as a result. So taking just my left-hand side, what's something I can do on the left side? I would probably try to write this using a common denominator. So I would have 1 plus sine x multiplied on the top and the bottom of the first fraction. And for my second fraction, I'm going to have 1 minus sine x multiplied on the top and the bottom. So now both my fractions have the same denominator, and I can add across the top. Be very careful adding across the top. We have a minus sign in the middle, so you have to make sure you subtract everything in the second fraction. So we're going to have a minus 1 and a plus sign. So I'm going to have 1 plus sine minus 1 plus sine all over 1 minus sine of x times 1 plus sine of x. So on the top, 1 minus 1 disappears, and I have 2 sine x. So my numerator is 2 sine of x. My denominator, I can distribute everything. This is actually the factored version of a difference of squares. When you distribute everything and combine like terms, 1 minus sine squared of x. We know this guy though. Sine squared plus cosine squared is 1. So 1 minus sine squared is cosine squared. Using that Pythagorean identity, I have 2 sine of x over cosine squared of x. And now we're actually almost done. I can just write this a little bit different. I have 2 sine x over cosine x times 1 over cosine x. I just split it up as multiplying different things together. And the only reason I did that is because I knew what my goal was. The right-hand side of the identity we were proving was 2 tangent x secant x, which is exactly what I have there using my quotient identities and reciprocal identities. So this one is also proven. We got to the right side just by manipulating the left side. All right, we just have a few more identities to verify, just getting our practice in. Let's verify 1 minus sine squared of t over 1 plus cosine of t equals cosine of t. So again, I'm going to take this left-hand side and manipulate it and hopefully get it to look like the right-hand side. So what I would do, I really don't like this second term here. Let me try multiplying that second term by the conjugate of the denominator, just because I really don't like that. So 1 minus sine squared of t over 1 plus cosine of t. Let me multiply by the conjugate of that denominator, 1 minus cosine of t. When I do that, in the numerator, I have my sine squared of t times 1 minus cosine of t. And in the denominator, I would get 1 minus cosine squared t when I distribute and combine like terms. But 1 minus cosine squared of t, that's one of our Pythagorean identities again. That's equal to sine squared of t, because sine squared plus cosine squared is 1. So I now have 1 minus sine squared t times 1 minus cosine t all over sine squared t. And then my sine squareds get to cancel out. So I just get 1 minus a 1 minus cosine of t. When I distribute that negative, the 1 minus 1 goes away, and I get negative cosine t, which is positive cosine t. And that was the right-hand side of what I was trying to show. So this identity also checks out. Let's do just 3 more examples, I think. Just get lots of variety in here, because unfortunately, even though these problems aren't too terrible, the hardest part about them is figuring out what algebra you want to do. There's no specific way for me to tell you how to do every single problem. So I'm just trying to give you a big variety to look at, and you'll just have to try different techniques on different problems and see if it works out. Sometimes things you try might go terribly wrong, and that's okay. That's when you just throw it out, start over with a new technique until you build up your instinct of what technique to use. So here's a different example for us. Let's verify an identity, natural log of the absolute value of cotangent x plus natural log of the absolute value of sine x equals natural log absolute value of cosine x. And what I personally would use on this one is use my logarithm properties. Hopefully you all remember those. When you have a logarithm of the same base and you're adding in the middle, you can rewrite that as a logarithm of the product. So on this left side, I have natural log of cotangent x times sine x. That's my left-hand side of the equation. Now, inside of the natural log, let me use my quotient identity to write cotangent as cosine over sine. And then the sign in this denominator will cancel out that sign, and I get natural log absolute value of cosine x, which is exactly what I was trying to show. So that one also checks out, just using properties of logarithms and our quotient identity. And let's just do one last example to finish this video up. This one's a little different. Let's write the square root of x squared minus 121 as a function of theta where 0 is less than theta is less than pi over 2 by making the substitution x equals 11 secant of theta. Now what we're doing in this problem is kind of a little preview into something you'll eventually do in calculus too, but we're not going into the deep details of it. But we will be doing things like this eventually in calculus. We're just getting us used to the idea right now. So they're telling us exactly what to do. We have square root of x squared minus 121, and they're telling us let x equal 11 secant theta. Well, let me just plug in 11 secant theta for my x and see what happens. Well, 11 secant theta squared is 121 secant squared of theta. And notice that under the square root, I have a 121 in both of those terms. So let me factor that 121. So I have the square root of 121 times secant squared theta minus 1. Now, the square root of 121 is 11. So I just have 11 times the square root of secant squared theta minus 1. What is secant squared theta? That's one of our Pythagorean identities again. Secant squared theta minus 1 is going to get me a tangent squared of theta. So then the square root of that tangent squared just gives me the tangent. Notice they told us theta was between 0 and pi over 2. Tangent of theta is going to be positive in that area, so I don't need to worry about the plus or minus or the absolute values that I get with squaring and square roots. So I just get 11 tangent of theta as that simplified version. All right, so that was a video of all sorts of different examples using our Pythagorean identities, reciprocal identities, quotient identities, and the even and odd properties of our trig functions. We are going to be learning some more trig identities in the next couple of videos and showing they're true by putting all of our knowledge together of all of these different identities. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in email or office hours or in class, and I'll see you guys next time.